Previously, we covered the core foundations. Now, in part 2, we tackle moon, surface, and interior. Last time, we looked at the moon as an object, its orbit, its distance, how it moves across our sky. Today, we go closer. We land. The question for this episode is, what is the moon actually made of? And what does that tell us about where it came from? That question matters more than you might expect. The moon isn't just a rock in the sky. It's a geological archive, one that recorded things Earth has long since erased. What's locked inside it, in its crust, its mantle, its core, still shapes the theories we hold about the formation of the entire Earth-Moon system. So let's start at the surface. That's where the story begins. The moon's surface is immediately strange, not in a dramatic way, just quietly, persistently wrong compared to what you'd expect. The first thing you notice in any high-resolution image is the sheer number of impact craters. They're everywhere, from microscopic pits on individual rocks to the vast South Pole Aitken Basin, which stretches roughly 2,500 kilometers across and plunges about 8 kilometers deep. One of the largest confirmed impact structures in the entire solar system. Earth gets hit too, of course, but Earth has plate tectonics, weather, erosion, water. It constantly resurfaces itself, burying or wearing away the evidence of old collisions. The moon has none of that. Every impact it's taken since its surface solidified is still sitting exactly where it landed. That makes the lunar surface a time capsule going back over 4 billion years. Scientists have spent decades learning to read it. The surface itself is covered in a layer called regolith, not soil in any biological sense. It's a fine powder of pulverized rock, glass beads, and mineral fragments, ground down over billions of years by micrometeorite impacts and solar radiation. Loosely compacted near the surface, more compressed deeper down. Apollo astronauts found it clung to everything: suits, equipment, instruments. Abrasive, electrically charged, and a genuine operational problem. Beneath the regolith, the crust varies considerably in thickness. On the near side, facing Earth, it averages around 30 to 40 kilometers. On the far side, it's considerably thicker, up to 70 or 80 kilometers in some regions. That asymmetry still isn't fully explained. It's one of the open questions we'll come back to. Now, the surface has two visually distinct regions. You can see them from Earth with the naked eye. The bright areas are the highlands, ancient, heavily cratered terrain, composed mainly of a rock type called a northocite, a pale, calcium-rich feldspar rock that formed when the early moon was largely molten. As that magma ocean cooled, lighter minerals rose and solidified into a crust. The highlands are the oldest surviving expression of that process. The darker areas are the Maria, from the Latin for seas. Early astronomers who named them thought they might actually be bodies of water. They're not. They're vast plains of solidified basaltic lava formed by volcanic eruptions that flooded low-lying basins between roughly 3.5 and 1 billion years ago. They cover about 17% of the moon's surface, mostly concentrated on the near side. Why the near side? That's the second open question, sitting quietly in this episode. The asymmetry between near and far side, in crust thickness, volcanic history, and composition, is something planetary scientists are still actively working through. The Maria tell us something important. The moon was volcanically active for a long time after it formed. It wasn't always the dead, static world it appears today. Something was generating enough internal heat to drive eruptions for billions of years. And that brings us inside. The interior of the moon is where things get genuinely interesting, and we know a surprising amount about it, partly because of the seismometers left behind by Apollo missions. Between 1969 and 1972, the program placed 4 of those instruments on the surface, and they recorded moonquakes for years. Moonquakes are real. They happen at 2 main depths, Shallow moonquakes, typically in the upper 100 kilometers or so, can be significant, some estimated at around magnitude 5. Deep moonquakes occur at roughly 700 to 1200 kilometers depth and are thought to be tidally driven by Earth's gravity. That seismic data, combined with more recent measurements from NASA's Grail mission, Gravity Recovery, and Interior Laboratory, which flew in 2011 and 2012, has given us a reasonably detailed picture of the moon's layered interior, working from the outside in. The crust, as mentioned, varies between roughly 30 and 80 kilometers thick. Below that is the mantle, which makes up the bulk of the moon's volume, composed primarily of silicate minerals, with olivine and pyroxene being dominant. The mantle divides into an upper and lower section, with the lower portion thought to be partially molten, or at minimum warmer and more ductile than the upper part. At the very center is the core. This was debated for a long time. Early analysis suggested the moon might have little to no metallic core. More recent work, particularly from Grail and reanalysis of Apollo seismic data, suggests otherwise. The current best picture gives the moon a small iron core, roughly 300 to 400 kilometers in radius, small relative to the moon's total radius of about 1,737 kilometers. The outer core appears to be liquid iron, the very center solid, broadly similar in structure to Earth's core, just much smaller in proportion. Crucially, the moon today has no global magnetic field, but some of the rocks Apollo brought back are magnetized. That tells us something once generated a magnetic field, possibly a functioning dynamo in the liquid core, that has since shut down. When and why it shut down is still an active area of research. The moon's overall composition is dominated by oxygen, silicon, magnesium, iron, calcium, and aluminium, the same elements that make up the bulk of Earth's mantle and crust, but in different proportions. Most notably, the moon is depleted in volatile elements, water, carbon, nitrogen, substances that vaporize easily at high temperatures, mostly absent or present only in trace quantities. That depletion is a very important clue. It feeds directly into the origin debate, which we'll get to in the next episode. Before we leave the interior, one more thing worth flagging. The moon does have an exosphere, not an atmosphere in any useful sense. No weather, no breathable air, no meaningful pressure. Subscribe so you do not miss it.